I'm just going to be quick because I already introduced Hans yesterday. So, Generalized Accounts and Hans Svensson. Round of applause. And go on.
Thank you. I will now try to explain what Generalized Accounts is all about. We actually built them already for the Fortuna release. So they've been out there for a whole hard fork or update cycle. But it hasn't so far been a tremendous success. There is not a single generalized account on the mainnet. So with this talk, I'm hope to change that, because I will show you that they are really powerful. You can do really fancy stuff with generalized accounts. This is the same slide as yesterday. I actually copy-pasted it. Well, yeah, exactly. I could maybe say 16 years of Erlang experience now. And I did start my Erlang career by pure chance. It's all Thomas's fault. I was doing my PhD on testing and verification, and I needed a case study. I needed a decently sized program that was sufficiently buggy, and he had written one, and it was in Erlang. Yes, Ulf also chipped in that process. So, from the top perspective, what is generalized accounts all about? In one sentence, instead of signing your transactions, you replace the signing or the signature with a contract that will authenticate your transaction. Sounds pretty simple. Why would you want to do that? It sounds also quite stupid, because the signature is there. It's cheap to check. You just sign your transaction and everything will work. But if you then want to change the signature scheme, you would have to convince the core developers to actually add another signature. You would have to change how accounts works. You would have to add lots of stuff. So it would be a complete pain, and it would actually not work very well. So the idea is that instead of changing the whole signature scheme, you just attach a transaction. You attach a contract, and that contract will do the signature checking for you. You will basically submit unsigned transactions, and there will be a contract that runs, and it will check whether your transaction is valid and can be run. And there are some special things with this contract, as I will show you. But in all, it's just a Sophia contract. You write a Sophia contract just like you would normally do. It has to follow one particular pattern, but apart from that, it's just a normal contract. So anything you can write in a Sophia contract, you can use to validate your transaction. But before we can actually look into what the generalized accounts does differently, we actually have to know how we sign transactions today. So this is a particular or a typical aeternity transaction. The simplest kind we have, it's a span transaction. I can point, yes. There is a sender. There is a recipient, 2 addresses. You send an amount of tokens, you pay a fee, you give it a time to live. You have to put in the correct nonce for this sender, and you can add some arbitrary payload to your transaction. Just a transaction, nothing fancy. How do we go about when we want to put this transaction on the chain? Well, first we need to serialize it, because this format is not what we have on chain. We have more compressed things which are just bits and bytes. So we need to serialize it. We do that, and we get the byte array. It starts by 12, of course, because 12, that's send. You know that already, yes? 1 is the version of the transaction, and then the rest is the compressed bytes and bits of the transaction. So we have that in a byte array. We add the name of the network to the serialization. We hash it. to get something that's of a fixed size, 32 bytes. And we sign that. So we in some way, we provide our private key, and we sign this byte array, and we get the signature. And in the end, we can now put together the actual transaction. What's ready to go on chain? It's the serialized transaction, and then the signature of the hash of the transaction, the hash of the serialized transaction plus the network name. And why is this good enough, or why is this how we do it? Well, there are three aspects of this transaction security here. First, well, we have to have a signature there. That's pretty obvious, because that means that it was the owner of this account that actually signed this transaction. Or maybe he lost his keys and someone else did it. But the idea is that whoever has made this signature had access to the appropriate keys for this account. We have the nonce there. This is to prevent replay attacks. If there were no nonces, you could take this spend transaction. If it was a spend to me, for example, I could republish it on the chain and run it again. It would be good for me, not so good for the person sending me tokens. And finally, we have added this network ID to the mix as well. It doesn't really matter that much now, but if there were to be a major hard fork, a real proper hard fork in the future of aeternity, you would have to name the true forks differently. They would have to have different network IDs, and that in that case you couldn't take a transaction from one fork and apply it on the other fork, because that would also be a replay attack. So that's why we have that. So these three things together make sure that the transactions is safe and secure. So with generalized accounts, we skip the signature. And we actually also skip the nonce on the outer level. But let's return to that later. So with generalized accounts, we have added to the protocol 2 transactions. The first transaction is called attach, or GA attach for generalized account attach. This transaction takes an existing account and attaches a contract to it, and thereby upgrading it to become a generalized account. Apart from having a different name, it is very similar to a contract create. It has virtually the same parameters, as I will show in a minute. So it's basically creating a contract and adding a pointer to your account, saying that from now on, I will be authenticated by this contract. And also, by doing this, we virtually cancel the possibility to actually use your private key for signing. So there's no going back here. If you tried, or if you decided to go for a generalized account, your account will be general forever. So there's no going back. You can't upgrade. It's a one-shot thing. So maybe you should test the contract first. And then once you have attached a contract to your account, then whenever you want to do a transaction with this account, you have to take or prepare your transactions just like you do normally, but then wrap them in a meta transaction, which basically takes your transaction, puts it inside another transaction where you run your contract, check that you actually want to run this transaction, makes it secure. I will show you exactly how it works. And then you can submit it to the chain. But first, the attached transaction. Again, lots of numbers, but I wanted a concrete example. So again, we want to now take this account we had before. We wanted to make it general. So we have the owner, the account that should be upgraded. We have, again, the nonce. So the attached transaction is a normal transaction. It has to be signed like every other transaction, because this account isn't yet a generalized account. You have to supply the contract, of course, But you also have to, and this is the special bit, you have to supply which function in this contract will do the authentication. We could have gone for a standard where you had to name it exactly authenticate or something, but we decided we can actually just give a pointer to the actual function. The rest of the parameters are the standard contract create arguments. You have to say which version of the VM and the ABI you want to use. You have to give it some fee, some TTL perhaps, a bit of gas, the gas price, and the call data for the initialize function. So this will just create the contract, initialize it, and then attach it to my account. And I have a generalized account. Yeah, now I want to use it, of course. So let's take more or less the same spend transaction I had before. But remember, now I'm a generalized account, so I want to use my generalized account signing. The sender is the same. It's actually the same recipient and the same amount and the same fee and the same time to live, but that just doesn't matter. What's interesting here is that now the nonce is 0. This signals that this is a transaction that should be authenticated by a generalized account. 0 is not a valid nonce for a normal transaction, so there's no risk of confusion here. So there's two things that has to be true. We have to have 0 as nonce, and this account actually has to be a generalized account. Then we still have to serialize the transaction. We have to add the network ID. We have to hash it. But then we can stop. We don't want to sign it because, well, the signature is not valid anymore. We now have to prepare data for our authentication function. And that data better have 2 components. It should better look at the hash of the transaction, because we don't want this. We don't want the generalized account to authenticate anything. You can make contracts that just says true for anything. That is virtually giving away all the funds of that account, because anyone can do a spend from that account. So to make this secure, you have to look at the transaction, and you have to handle the nonce in that contract. So in this case, I have some fictitious function here, which actually prepares this authentication data for me. It's maybe not entirely straightforward how to do it, but it's pretty easy. And since I just created this generalized account, well, the nonce is 1. So for here, when we made the attach, we actually used our old nonce, the nonce of the account. But then once we transfer into the world of generalized accounts, that nonce is no longer valid. So we have to start over. We could take our contract and set the nonce to whatever we like, but maybe starting from 1 is a sensible choice. So that's what we did. So yes, there. And then once I have prepared this authentication data, as I mentioned before, we have to wrap it. So we take one of those meta transactions, we put this authentication data in there, and we also build, for technical reasons, a signed transaction without the signature. So we basically put the serialized transaction in there, but without signatures. And this is ready for the chain. So what will happen when this transaction reaches the mempool, or when the miner wants to include it on the chain? The miner will take this transaction. He will see that it's a generalized accounts transaction. He will take the account of this transaction. It's in the meta here, metadata, or in the meta, or the data of the meta transaction, sorry. He will look up this account. He will find out that it is indeed a generalized account. He will look up the contract, and he will call that contract with this authentication data, and it will also give it the hash of the serialized transaction. And then that verification function should run. I will show you an example of such a function in a short while. And if it's successful, we will just apply the transaction which we put into our meta transaction. It's a bit involved when you look at it like this, but all of this is, of course, taken care of by the tools and the SDKs and then whatnot. And Emil is laughing. Well, there is some tool support still missing, but it soon will be there. And then this will be not much harder than just signing a transaction normally. You will just supply basically the same data. There are a few limitations to this, because if there were no limitations, then the generalized accounts authentication function would virtually be a contract call. And that would mean we would have to price it as a contract call. And contract calls are a bit expensive. So by making some limitations, we are able to make them slightly cheaper, or quite a lot cheaper, which is better. So the miners will restrict the gas that a authenticate function can use. So no more than 50,000 gas for your authentication. And you also can't do any chain operations in the authentication function. So you can't spend your funds, you can't create oracles, you can't register a name, and some other operations. For a good reason, they really have nothing to do with authentication, but just to make it clear. So let's also look at a very concrete example. Everyone knows the SEC-P256K1 elliptic curve? Yes, good. It's the one that Ethereum and Bitcoin uses. So we will build a contract here which will use the crypto of another curve, and most of the other, or many other blockchains use this curve. So we'll use the crypto from this and use it to sign transactions on aeternity blockchain, which is quite nice. And there is actually a use case for this. Many hardware tools or hardware signing tools only work with this elliptic curve. It's for some reason, or I think it's just a matter of optimization. There are more optimized implementations of this curve, so they fit better into hardware. So if you have one of those tools and you want to make use of it to sign transactions for eternity, well, you better have a generalized account. So, yes, I already said that. This is the elliptic curve. So, Sophia code, the contract. It's fairly straightforward. To be nice, we define a few types. We define the type of an Ethereum address, and it's 20 bytes. So one of the addresses on Ethereum is 20 bytes. The signatures are 65 bytes, so we have a type for that. The state of this function, remember we have to keep track of the nonce, so we have to have a state so we can update it. It consists of a nonce and also the owner of this generalized account. So when we attach the contract, we will run the init function and we will set which Ethereum address actually owns this account. And as I mentioned, yes, we start with the nonce 1. That's sensible default in this case. Then there are also a couple of helper functions. We have an entry point which says what do we actually sign, and in this case it's just the pair of the hash and the nonce. So as I mentioned before, in order to keep this secure, you need to make sure that you're actually looking at the hash and also the nonce. Otherwise you could replay it, or you could make it authenticate any transaction. And there's also a convenience function to access the nonce if you have forgotten how many transactions you have already signed with this account. You can get hold of that. So far, nothing very strange. And then comes the magic bit, the authenticate function. Hey, still not that complicated. It fits on one slide. I didn't even have to make the font smaller. I mean, that's the normal trick when you get into a talk and you gradually get to more complicated stuff. The font gets smaller and smaller and smaller in order to make it fit on a slide. But no, I actually managed. I did have to stretch it a little bit over here, but I think that's fair. So what are we doing? We have the authentication function. It's called auth in my case. It takes two things. It takes the nonce and it takes the signature. And this is the Ethereum signature, or the Bitcoin signature it could be as well. And this has to be done on the outside somewhere. So this is something you provide in the authentication data. This is what you would do with your hardware wallet or hardware signing tool, however that happens to work. But once it reaches the contract, we first check two things, namely that the nonce is not too low and that it's not too high. And if it's not too low and not too high, well, then it's perfectly the same. These two lines of code has caused some confusion. Yeah, Dinch has asked, Alexander has asked, Thomas has asked. But yes, we check that it's not too high and it's not too low. That's the same thing as checking that it's equal, but the error message will be much nicer, and I always care for my users and give good error messages. Sorry. Then, as I said, we need to handle the nonce. So of course we should update the nonce of the state and record that we have actually used this nonce. So we put it in the state, and then comes the magic bit, or the magic bit. This is what's new and strange. When you are running, or when you are authenticating a generalized account, you are in a special execution context in the Sophia contract, or in the VM. Namely in the auth context. And if you are in this context, you can look up the transaction hash of the thing that you're trying to authenticate by saying auth.txhash, and if you're in the correct context, it will say some txhash. This is the option type of Sophia. And if you're not in this context, it will simply say none. If you're trying to run this outside of an authentication, it will just say none here, and it will abort and saying, well, you're not in the correct context. Go away. But if we get hold of the transaction hash, we will use the crypto operation from the correct curve and check whether it's actually this contract or this address that has signed this transaction. So 2 pages of code, and that's it. That's all you have to do to use the signing from Ethereum or Bitcoin or any other place that uses this elliptic curve. And you can use it on Eternity. Pretty neat, right? Yeah, so we had a few use cases in mind, or especially this one with hardware wallets and hardware signing tools when we designed this. But you should also use this for wallets, typically, because this is the way you can actually run arbitrary calls from a wallet. And this is a contract in there. You can add all sorts of fancy things like spending limits, multi-signatures, whatever. And I'm also thinking that you could use this to some extent for giveaways. You can actually publish a contract there that will always authenticate in some way and will slowly give away your funds or something. And some other campaigns. We've also been discussing the last couple of days that you could use this as a way to pay for transactions. Though there is a little bit of a problem with that. If we looked here, we only got hold of the transaction hash. And as I've explained a couple of times to Thomas, there's no really good way to get from a hash back to what you actually hashed. That's kind of in how hashing works. So there's no way to actually know in the contract what the transaction is about. So we have a plan to extend this further by saying maybe you can do auth.tx and get the hold of the whole transaction and some plumbing for Sophia to actually inspect the transaction. Should be a pretty straightforward addition, and we are planning to do that for the next hard fork or for the next update. Sorry. And there are possibly other applications as well. I've just built it. If it's a hammer, you can use it as a hammer, but there are probably other ways to use it as well. Further development, as I said, we talked about adding more context to content to the auth context, maybe the full transaction. We have also plans to add more primitives of more crypto primitives, zero knowledge proofs, more fancy multi-sig, Schnorr signatures. Sasha is in charge of all of that. He will give me a list and I will just add it. And if I have time, I will also try to understand a bit of it, but mainly I will add it. And then finally, an important piece of this puzzle, which we actually already have done. You can now, from the Lima update or the Lima release, you can actually dry run this. Previously, there was no way to dry run something in an authentication context. But now you can either give the full meta transaction, or you can actually say to the dry run that you want to run it in an authentication context, and you give the transaction hash of the transaction. So with that, I think I'm more or less done. This is Generalized Accounts. Thank you.
Right. Let's do 2 questions. I see 2 hands. Go on.
Yeah, first of all, I think it's really a fantastic feature, and I'm pretty sure it will be used in the future. I have 2 questions. So how hard is it to actually add those other crypto primitives, or like kind of, is it on like, how can people contribute to kind of for more interesting GAs? Like now we have Ethereum and Bitcoin.
Yeah, no, you have to do it at the core level. They have to go into the virtual machine. They have to become operations of the virtual machine, unfortunately. So it has to be done in a hard fork or an update. Okay. Actually doing the implementation of them or adding them to the VM is pretty straightforward, but it has to be done on that level.
So if basically users would request this on GitHub in the forum, explain a use case why this makes sense, and then
then once the primitives are there, then of course the users can contribute contracts that actually combine the primitives in interesting ways.
So I'm currently speaking to actually a couple of smaller governments that all more or less launching their digital ID cards for their citizens. And I was thinking that maybe, I mean, they're not all that open, but there are some countries like Estonia or also Liechtenstein now, because it's small countries and so on. And I think this would also be a very nice, cooperation with them to basically enable signing with these digital ID cards of countries for accounts, for example.
Yeah.
Okay, there was another one. He was first. Go on.
I have a couple ones, but they're small. Who's paying for the gas, and is the meta transaction paid? And how much does it cost to deploy your generalized account?
Who's paying for the party?
The generalized account costs about the same as a normal contract.
So when you're deploying it, you have to also pay for this transaction.
Yes.
And then when you're doing the meta transactions, who is paying for them?
The generalized account.
So you have to have some balance in the generalized account so that they pay the miners.
Oh, yes.
Okay. And second thing, maybe I did not understand it or correctly. How do you actually pass the nonce in the Ethereum signature in the transaction? I think you had it somewhere in the slides.
Yes. So no. Let's see. No. There. Animations. It's part of the authentication data. This is like the call data of the generalized account, and in there you pass the nonce.
So hash TX is probably going to also have the signature that's signed by the Ethereum wallet.
Yes. The authenticate. This function here will do something like Ethereum signing.
Okay, thank you.
Okay, one more, Sergey. And then we'll move.
I had two, but first was just answered. The second one, do you know? I think we have it in both a EVM and a Fade, right?
Yeah. It's just a contract.
Do you know like how contracts like this were affected by the transition to Fade, like the size of the bytecode, the performance?
Yeah. So it will be cheaper to create them on Fate, and it will be cheaper to run them. So you can fit more in those 50,000 gas on Fate.
Yeah, because the function looks like pretty small, so not too far away from this identity function. So the bytecode got much smaller.
Yeah, this will be really small, and it will not cost very much to execute.
Nice.
Okay, I also actually got two questions. The first one being, how do you stop someone from draining your account? So you got a generalized account with, let's say, one IE token,
Yep.
and I'm a spammer, and I'm writing a script which will which will spam meta transactions in a way which is most expensive for the user.
Well, you only pay if this function returns true. So the spammer has to figure out a way to sign with your key, which it probably can't. So
okay, so I've got the follow-up question for that one. How do you stop someone from spam flooding the network with expensive operations? Because, for instance, what would happen if someone would write a generalized account in which spams AC recover a lot, which is pretty expensive, and then someone spams meta transactions?
It's not that expensive. But yes, no.
But what would happen if an attacker creates a malicious generalized account and then spams really expensive meta transactions?
Well, that's why we have this limit of 50,000 gas, which isn't that much.
Okay.
So that's the only way we can stop them, because we can't really charge for if it's false, like you said. Then the spammer will drain your account. So instead, the spammer might annoy the miners, and I guess the miners should be able to filter this somehow. But then they know they would have to implement something.
Okay, thank you.
Any more? We have a good discussion going on. No? Okay. Oh, yeah. No. Wait, don't clap.
Well, it's a follow-up question on the same thing again. So if it fails, it will not cost anything.
Yes.
So, but does the same apply to any contract?
No. Normal contract executions, you will pay for the gas even if they fail. But in this case, since it's not signed, we can't really charge.
Okay, I think Hans deserves a big round of applause for that.
Thank you.